Okay, Calc 4, Lecture 21, General Vector Spaces Dimension or Dimension. Now, two facts. Suppose the set S with n vectors is a basis for a vector space V, which means that this is an independent, linearly independent set, and it spans V. Then, one, a subset of V with more than n elements is not linearly independent. We had something like this in previous section. Number two is a subset of V with less than n elements does not span V. So, if I have n plus 1 elements of V, just gather them in a set, and we have assumed that this is a basis for V, then the other set, which has, say, n plus 1 elements, is not linearly independent. Two, if I gather, say, n minus 1 elements, one less than that, then that set does not span V. Okay, so these two, they result in an amazing theorem in linear algebra. This is the dimension theorem, one of them in fact. There's another one by this name theorem. Any two bases for a finite dimensional vector space V, any two bases have the same number of elements. So finite dimensional means we can find a basis for V which has finite number of elements. Okay, so if we can find that, then we call this finite dimensional. Then this theorem says if you find another basis for this vector space, it should have the same number of elements. So let's, we can use these two to prove it in fact. So suppose this S, we have found S to be a basis for V. And somebody gives me another set, S prime say, which has less elements. And he claims that that is also a basis. So let's say he gives me a set which has n minus 1 elements, and he claims that it is also a basis. Now how can I show that the claim is wrong? Two, I say, okay, if you give me less elements, a set with less elements, it does not span V. And when it does not span V, it cannot be a basis for V, because basis spans V. Someone else gives me a set which has more than n elements, and then I refer him to this one and say, okay, the set that you gave me is not linearly independent. Therefore, it cannot be a basis. So, if you give me a basis, other than that, it should have exactly n elements. Okay? So, it seems that that number n is some kind of attached to this vector space. So, no one can find more or less, a basis with more or less elements. So, that number n comes with V. So when you are given a vector space, and if you can find one basis set with n elements, then that n is attached to this. It's like a flag given to this. When you look at V, you immediately say, yeah, I know, this n is something attached to this. It's like on its face. Okay, well, this n, which is attached to this V, it's like we say it's invariant. So this number, we call this number dimension of V. Okay, so let's use this theorem, which comes from these two facts, and define dimension. Definition. Given a finite dimensional vector space, V, the number of elements in any basis of V is called the dimension of V, denoted by dim of V. Okay? So why is this well-defined? Well-defined means it doesn't change with different bases because it depends on basis. It depends on the basis and the number of elements in each basis. Well, I refer a person to this theorem. If you give me any basis, that basis should have the same number of elements as the one which I found, for example. So if someone can find a basis for V and it has n elements, that's it. Any other basis should have n elements. And that n will be dimension of V. So this also means that if you can find one set, one basis set, then that gives you, not just it gives you basis, it also gives you the dimension of this space. Okay, let's look at some vector spaces and the dimension for them. So, examples. One is Rn. Rn basis for Rn is, basis is this E1, remember what EI's were, E2, En. Remember the EI is the standard basis. And so how many do we have? N. So dimension of Rn is in fact n. But this n in fact comes from the dimension. Number two, what else did we study? So that was M matrices, M by n. Matrices M by n. Well, a basis is like this. So a basis is something like matrices like this. So it's a matrix, say Aij M by n, such that just one of them is 1. The rest are 0. All zeros except 1 and 3. So these are matrices with all zeros, everywhere 0 except one entry which is 1. With one entry which is 1. Okay. So how many such matrices do we have? For every row we have like n, column m, so we have m by n, m by n, so the total is m times n, in fact, m times n. So we say the dimension of m by n is m times n. So for example, dimension of m 2 by 2 is 2 times 2, which is 4. Okay, so these are the two that we started with. Okay, now let's look at other examples. One, two. What was the other one? I can't remember. So the other one was. Oh yeah, the polynomials. Number 3, Pn x. We know that this is in fact a basis for this. Basis is this 1, polynomial 1, then x squared up to xn, right? Any polynomial with degree n is a linear combination of these. How many do I have? This is n plus 1, not n. So dimension of Pnx is in fact n plus 1. What else did I discuss? Okay, so let's look at this. Let's look at something like this. Let's say V is a subset of, say, it is well, let's say A11, A12, 0, A22, right? And Aij's are in odd. So what is a good basis for this? Well, it's very easy to find a basis. So basis is the matrix which has 1 here, and the second one has 1 here. There is no 1 here, so the third one will be 0, 0, 0, 1. Now, these are linearly independent. It's very easy. Just write k1, k2, k3 equals 0, and all of them will be 0. And there's nothing here. It stays at 0. This third one, this entry stays 0. And they expand this thing. Like this one is A11 times this plus A12 times this plus A22 times this, right? So what is the dimension of this V? The dimension of this V is 3. So the dimension of V is 3. And I didn't have to find any other basis. As I said, just find one basis. So let me maybe, let me write it A11, A12, 0, A13. If I call this, say, U1 and U2 and U3, then this will be A11U1 plus A12U2 plus this is not 22, sorry. This is 22 plus A22U2. Okay? So this is in fact a linear combination of those 3 matrices. And they are linearly independent. Just write this equal to 0, you will get 0 everywhere. Okay, so that's how you just assign dimension by finding a basis, and then that basis will be the number of elements in that basis will be the dimension of that space. Now let's look at the function spaces. Let's look at the function spaces. Remember, I had the function spaces. There was one function space which was, say, C infinity, minus infinity, and infinity, which was functions that are infinitely differentiable. Now, inside this, every p and x was inside this for any n. And remember, all functions was included everything. So all functions, single variable functions, includes everything. So the pn's are inside this. And for any n, pn has dimension n plus 1. Pn plus 1 has dimension n plus 2, and so on. Well, this n can be any number, right? And for any number, this is inside this. So this C infinity cannot have a dimension n or n plus 1 or n plus 2. It should have dimension a lot more than that. In fact, we say that this one it is not finite dimensional because you cannot write any one of them as a linear combination of polynomials, finite degree polynomials. In fact, you can also show that one of them, e to power x, which belongs to c infinity, minus infinity and plus infinity. Remember from Calc 2 that you can write e to power x as what? It was sigma, what was that, n factorial, and that was x to power n factorial, and the n goes from 0 to infinity. So it was like this. 1 plus x plus x squared over 2 factorial plus x 3 over 3 factorial, and so on. So you see e to power x is in span of what? E to power x seems to be in span of this 1, x squared, x3, and so on. It doesn't stop. The Taylor series doesn't stop, goes to infinity. So e to power x is a part of this span, not equal. It is an element of this span, and this set is not finite. This set is not finite. So e to power x cannot be written as a finite polynomial. It's not a linear combination of some finite polynomials. I mean, finite degrees. How should I say that? Yeah. So this should, e to power x includes, let's say it this way, e to power x includes any polynomial of any degree, any, say, xn, for any n. So this guy here, c infinity, cannot be finite dimensional. So that's an example of a vector space which is not finite dimensional. Therefore, this one which includes everything is definitely not finite dimensional. So function spaces are not really, in that sense, finite dimensional, except the PNs, which are just finite degree polynomials. Okay. So let's look at the dimension of solution space of some system of equations. Let's go back to the system which I had, 1, 0, say minus 2, 5, 8, and 0, 1, and this is reduced, so you should reduce it anyway, and say 3, 10, and negative 12, and times x1, x2, x3, x4, and x5 is 0, 0. Okay, so what are the options for parameters? So parameters will be R, say, S, and T. So R, S, T. So x1 minus 2r plus 5s plus 8t is 0, and the second one will be x2 plus 3r plus 10s minus 12t is 0. And this gives me, let me write it, x1, x2, x3, x4, x5, and so this will, I should take this to the other side, so it is r times, when I take it to the other side, I have 2 here, this is minus 3, this is 1, 0, 0, how many? 0, just 0, 0, right? So that's 5. Plus s times minus 5, and here this goes to the other side, minus 10, 0, 1, 0, plus t times minus 8 here, and 12 here, 0, 0, 1. Okay? So, I can say the solution space of this system Ax equals 0. So solution space Ax equals 0 is in fact span of these vectors 2, minus 3, 1, 0, 0, and come on, minus 5, minus 10, 0, 1, 0, and the last one will be minus 8, 12, 0, 0, 1. Remember, I showed that vectors like this, which are, say, 1, 0, 0, 0, 1, 0, blah, 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 after a certain point, like this. You see this? 1, 0, 0, 0, 1, 0, 0, 0, 1. These are linearly independent. And I showed for one of them, you can just write down any number of them and show that in general, that any set of vectors like that is linearly independent. And they span, I have written that, I have written the solution space as span of a certain vector. So this shows two things, which in fact I discussed that. Span of some vectors is a subspace. 2, this becomes a basis for this. So this set, this becomes basis for the solution space. Becomes a basis for solution space. So what does it mean? It means that this solution space, not just it is a subset or subspace of R to power 5 subspace. What is the dimension of this? With dimension equal to 3. So the solution space of this system of equations is a subspace of R5 of dimension 3. Okay? So if this is R5, say, then this is the solution space. That is part of R5. R5 has dimension 5, this has dimension 3. Okay, so that is how you find dimension of a solution space. And from now on, I prefer to call this solution space, but sometimes I just call it solution set. But you can see that it is really a vector space, and you can find it's a basis for that. When you solve it, it just comes out. So the way that we solve it, in fact, ends up with a basis set. So this is basis set for this solution space, and counting the number of basis elements, you can that is in fact the dimension of your solution space. So that is also example of solution spaces and the dimension of solution space. Okay, now there are some theorems here which I have to mention. Yeah, this is in fact another important theorem, and I mentioned, I guess, last time how the basis helps here. Suppose we know that dimension of V is n, right? Then a set S U1, U2, Un is a basis for V if one, it is linearly independent or 2V is span of S. So this or, let me put the circle, this or here, it means that 1 is enough. This or means 1 is enough. Why 1 is enough? Because this has n elements. It has n elements. So this has n elements. Okay, so let me say it again because this is crucial. Remember when we wanted to check, see if a set is a basis, we had to check both of them. We had to check and see if it is linearly independent and also check that it spans. And I told you back then that one of those is enough in a sense. Well, anyway, so this is in fact that theorem. It says, okay, if dimension of V is n, and I have a set with n elements the same, then this set is a basis for V if one of them can be verified. Either that set is linearly independent or it spans S. Now, if you showed both of them, that's okay, but that's too much work. Why? Why should you do that? Most often you will see this one, that's why I wrote it first. It's easier to show this one is linearly independent. I mean this first one, to verify first one than the second one. Although they are in fact related, that's why one of them is enough. Okay, so let me give you an example of this. Example. So let's take S to be this subset of 1, 0, 0, 1, 1, 0, and 1, 1, 1. This is a subset of R3. So is this a basis for R3? So is S a basis for R3? Is S a basis for R3? So solution is this. Since S has 3 elements and the dimension of R3 is 3, we have to check, we check its linear independence. Linear independence. We check its linear independence, okay? As I said in the theorem, either show that that set is linearly independent or it spans. It's easier to show that that set is linearly independent. So let me erase this and show that it is linearly independent. So what should I show for linear independence? I should write this linear combination K times 1, 0, 0, K1 plus K2 times 1, 1, 0 plus K3 times 1, 1, 1, and that should equal to 0, 0, 0. So let's write them in the other format. So the first one is K1 plus K2 plus K3 is 0. The second one is K2 plus K3 is 0. The third one is simply K3 is 0. Oh, okay. So that's it. From here, I have K3 equal to 0. I put 0 here. This gives me K2 equal to 0. Then put 0 here and here. So this is 0 and this is 0. This gives me K1 is 0. So S is linearly independent. No, well, the terminology that I use for definition, I use this terminology that a set is linearly independent. I might have used this terminology saying that these vectors are linearly independent. They both mean the same. Okay, so I showed that this S is linearly independent. Therefore, by the theorem, the theorem that we just explained, S is a basis for R3. So if S is a basis for R3, this is a crooked R3. Okay, so as you see, I just checked one thing, and that is linear independence. It's much easier to check that one. Well, sometimes the other one comes into the picture by just naturally. I cannot recall a situation like that, but this one happens more often. So, in fact, this also shows that at least there are two sets of bases for Rn. One is the set of those standard bases, the EIs, and the other one is this one. So the one is ijk and the other one is this one. This wasn't ijk. The first one was I, but the second and the third ones were not I, j or k. Then we have other theorems. This theorem is the W be a subspace. This is also, again, I used it, but as you see, I just put the stars on top of every one of them. So let W be a finite dimensional vector space. So V is finite dimensional. So for finite dimensional, you can either find a basis which is finite, or you can find a subset of V that spans V. That's enough. So it doesn't have to be basis. If it just spans, that's enough. Okay, so V finite dimensional, W in V is subspace. Okay, so what do you think about the dimension of W? Is it less than or bigger than or equal to V? So the dimension of W is, in fact, but first of all, W becomes finite dimensional. Two, dimension of W is less than or equal to dimension of V. Dimension of W is less than or equal to dimension of V. You might say, why equal? Equal is because I have put equal here, which means that this W can be V itself. And remember I said subspaces, V is a subspace of itself. We consider V as a subspace of itself. Now this one proves something. 3. W equals V if and only if the dimension of W equals dimension of V. That is something. That is in fact something. You see, in mathematics, it's not easy to prove that two entities are the same. Equal is the same. It's not easy to prove that two entities are the same. This theorem tells me just check the dimensions, and if one of them is inside the other one, then they are the same. The same means that it's like you find one element here and another one in the other one which are the same. Then here, same. That is hard. But this theorem, in fact, is telling me, no, it's not that hard. Just find dimension of each one. If the dimensions are the same, then they are the same. So this is in fact one of the things that this dimension idea gives us. It can give us a way to show that two vector spaces are in fact the same, and one of them inside the other one. It also shows something else that that's not in this course, but anyway, it shows that if this happens, then W and V are in a sense they're isomorphic. They're like the same vector spaces. They might be from two different, say, planets, but they are the same vector spaces. So let's see. Example. Remember P3x. I don't know if I gave you this as an example, or maybe I made a mistake. So this is like span of what? Span of 1, x squared, and x3. So dimension of P3 is 4. Now let's say W. Let's say W is span of say 1 plus x, 1 plus x plus x squared, and 1 plus x squared plus x3. Okay. So what is the dimension of W? Well, dimension of W is 4. You can check that. You can check and see if they are linearly independent. So let's check. So K1 times 1 plus K2 times 1 plus x plus K3 times 1 plus x squared plus K4 times 1 plus x squared plus x3. And this is the same as 0 polynomial. I wrote equivalent. That is the same as that. This is not say, equation. It means that they should be the same. This should be the 0 polynomial. Okay, so what do I have here? I have K1 plus K2 plus K3 plus K4 times element 1. There's 1 here, 1 here, 1 here. Plus K2 plus K3 plus K4 times element x. Plus K3 plus K4 times element x squared. Plus K4 simply times element x3. And this is the same as 0. So it means that the coefficients of this polynomial on the left should be all 0, because coefficient of this is in fact 0 plus 0x plus 0x squared plus 0x3, right? So this should be 0, this should be 0, this should be 0, and this should be 0. So if I write them here, I have K1 plus K2 plus K3 plus K4 is 0. I have K2, K3 plus K4 is 0, K3 plus K4 is 0, and K4 is 0, right? 0, this one is 0, then put here K3 is 0, 0, 0 will give me this one, 0, 0, 0, 0 will give me all of them 0. So K1, K2, K3, K4 are 0. So this set, this shows that this set, let's call it S, is linearly independent. So being linearly independent, and we know that this W is a subset of, or subspace of P3. It is a subspace of P3. P3 has dimension 4, this one has dimension 4, so dimension of W equals dimension of P3, right? And this is 4, this is the other one is 4, so this tells me that W is in fact P3. W is in fact P3x. Which also means that these four vectors can be considered, or this S can be considered a basis for P3. But it's not a nice basis. This is a much nicer basis. Why should I use this thing? But anyway, that is, you might say we could have given another argument for this, but well, I just refer to that last theorem, the third part of that last theorem. So let me see if anything else is remaining from. Okay, so that was dimension, and we saw some finite dimensional spaces like Rn's or Pn's, and we saw some like matrix spaces which are like n by n, and also some infinite dimensional, which are like C infinity or F function spaces, except for polynomial spaces. The rest of them are basically not finite dimensional. Okay, so let me stop